Now that we've decided how to do our redox titration, we want to walk through what the experiment is actually going to look like. So I've decided my platinum 2 chloride solution, there's platinum 2 in there. I'm going to oxidize it to platinum 4 using the oxidizing agent KMnO4, potassium permanganate. So I start by putting my platinum 2 chloride solution in just my flask. I do want to use a precise volume because the whole goal is to get a nice precise concentration. Part of that is the volume, so I want to be careful measuring out a precise volume. So 23.18 milliliters of the PtCl2 solution. In the burette is where I put the KMnO4. I know what the concentration is, and again, I want to be precise. I want to measure these things, as exactly as possible. Do all my measurements as carefully as possible to get a nice amount of sig figs functionally on the concentration. So 0.105 molar KMnO4 is in my burette. The thing to remember is that I'm dealing with salts in all of these. So even though I'm writing out these full compounds, when I'm writing out the solution name, in the actual solutions, they are separated ions that are floating around, right? The chlorides are floating around independent from the platinum 2s, and then the potassiums are independent from the permanganates in the burette. And the ions react with each other to do the independent or unique chemistry that's going on. All right, so set up. Time to start adding my KMnO4 to the flask. So just put some in, the ions stay separated, and now they're going to react. The whole point of the MnO4 minus was to be a oxidizing agent to oxidize that platinum. And so we can look up the half reactions for each of these and balance them. I'm not going to use stoichiometry or I'm just going to say that the MnO4 I know is going to become Mn2 plus, and the platinum 2 plus is going to become a platinum 4. So this is not following stoichiometry, but I'm just going to change the names of the symbols of the formulas in my flask. So chemistry happens, and they're different, right? I have the platinum 4 and the Mn2, the products that are starting to show up. And we know that the whole idea of a titration is I keep adding the KMnO4 until all the platinum 2 plus has reacted, right? Until all of it is exactly gone, which I call the equivalence point. So how do I know when I hit it? These are all just solutions. They don't tell me when I hit the equivalence point. So how can I figure it out? So this is why we use a lot of transition metal cations. Transition metals oftentimes are brightly colored when they're in solution, and different oxidation states show different colors. So if you remember, the two most common oxidizing agents that we use in these titrations are manganese and cerium. And so the reason for that is that we start with manganese, this MnO4 minus. The manganese is in a +7 oxidation state, which is purple. When it goes to a +2 oxidation state, it's colorless. Similarly, cerium at +4 is this golden yellow color, whereas at +3, it is colorless. So what that means is that the color change that we want to see for the reaction, for the titration, is the actual just compounds in the titration. We do not need to use a separate indicator molecule. The actual manganese or cerium, whatever you're using, functions as the indicator. So that's why these two particular ions are so commonly used in redox titrations, because they're really good oxidizing agents, and they have these really bold color changes from really boldly colored to colorless, which is important. You get a nice strong change. It's not like purple to green, where you get kind of some brown mix or something. It's purple to colorless, golden yellow to colorless. So when you have the MnO4 in the burette, it is purple. Those letters are supposed to be purple. It is very dark purple, so I may have gone a little too hard. But so they are purple in there. And so when you add the MnO4 into the flask, it is purple, but it reacts with the platinum that's present and becomes the colorless Mn2+. So basically the idea is you started with platinum 2, right? And you're adding in this purple MnO4. And as long as there is platinum 2 in the flask, it'll basically cancel out the purple. You're adding in purple, but it reacts and becomes colorless. Once the platinum 2+ is fully reacted, if you add more MnO4-, if you add more purple, the flask is going to stay purple. And that's how you know you're done. So when you're actually running this reaction, the MnO4, this is a real life photo. You can see the burette, it looks almost black, right? It looks opaque. This stuff is an extremely potent purple dye. So when you're like actually doing these experiments, you'll note this person is wearing a glove because it will stain your hand purple for a very long time. It also can oxidize your hand, which isn't good for your hand. But so this stuff is very, very bold, very dark purple. During the titration, the purple is the reactant. It gets into the flask and you can see it fades out because it's reacting with the platinum. The purple reactant becomes the colorless product. Okay, so that keeps happening. Eventually, the flask will have a little bit of purple left in it. You'll see it's really faint relative to the burette, right? The burette looks black. Even this, where it's like a real thin in the nozzle of the burette, it still has a purple color. Basically what happened is you get the minute, or once you start to get some lasting, very, very faint purple, you have basically really dilute MnO4. And that's how you know you've reached that equivalence point, because not all the purple is just getting wiped out. Those reactant molecules, that MnO4 is left over because you have reacted everything that was in the flask initially that was reacting with the MnO4- to produce that colorless product, Mn2+. So you can see, here's a nice little GIF of it where you can see the purple goes in and then the person shakes the flask and it goes away. And actually you can see this is a nice photo because it shows, you'll see it's purple and then sometimes it looks like there's like a brown flash. It's purple, brown, then colorless. That brown is Mn4+. So basically you're going from the +7 oxidation state to the +4 oxidation state to the +2 oxidation state, which is colorless. And so that's why we actually want to push it the whole way, because we want to get it fully colorless, right? You're going, basically it's easy to see what color is here when it's relative to, you can see that faint purple when it's relative to no color at all. It's harder to see faint purple relative to brown. So it's kind of muddy. So that's why we use this manganese in this particular way, because we have purple to colorless. And it's easy to note, it's easier to see that little bit of purple that starts to show up against the colorless background of the Mn2+ that you were forming. Okay, no participation questions in this video. It is the halfway point though. So halfway through this set of videos, we're looking for any more questions for participation 4.3. See you in the next video.